Thanks, Jason.
Great. Thanks, Bob. So I'm going to start with just a few drivers for recycled water and biosolids use, what causes a municipality to consider this option amongst all the things it could consider for treatment. Share a few slides on typical loading rates, nitrogen and hydraulic loading that we use in the Northwest, and then a few ideas to maximize tree system performance. So this is a map of total maximum daily load development status in Oregon. The same story applies to the rest of the states in the U.S. really, but as regulations develop, permits don't become less stringent due to anti-backsliding rules. They only become more stringent. So every new permit cycle comes with more limits. And some of these load-driven limits are starting to drive down to limits that test the technological limits of wastewater treatment. In that case, recycled water use becomes an obvious option. So here's one example from City of Woodburn. Curtis is going to talk about more of this later, and you might join the tour also. But just briefly, this is a good example of that. With TMDL in 1993, there was a new mass load limit for ammonia discharged to the Pudding River. To allow continued full discharge of the plant flow in the summertime, you would have to treat ammonia down to below 0.1 milligrams per liter on a monthly average basis, which is difficult, if not impossible, to reliably do, and very costly to approach that limit. With that mass load limit, though, if you look at discharging a lower volume, so this chart here is showing at a discharge greater than 2 MGD, you have to treat down to 0.1 milligrams per liter. If you could keep your discharge down below 1, you only have to treat up to 1.5. To be able to discharge up to 2, but no greater, the limit is 0.5 milligrams per liter. That's something that's achievable in the plant with an advanced secondary wastewater treatment facility. So with that limitation, though, of no greater than 2 MGD, that excess can go to some other out-of-stream recycled water use, and that's the opportunity here. There are a lot of options for recycled water use if you look at getting that water out of stream. Most secondary treatment facilities are producing a Class D water, secondary treatment with disinfection. And poplar tree irrigation is one of the allowed uses in Oregon, along with other non-food crops. If you wanted to be able to apply that water for non-potable irrigation use in a unrestricted public access setting, a golf course landscape, you'd have to install additional treatment to get up to a Class A standard recycled water that requires tertiary filtration and advanced disinfection, which is an additional cost and additional operations issue at a facility. So one of the benefits of poplar trees, in this context is that Class D compatible use, low maintenance and infrequent harvests. Most of these systems are, they're being operated within a larger wastewater treatment facility, and usually the staff is focused on wastewater treatment and meeting permit limits, discharge limits. So something that's easy to separate some of those activities of the tree management, make it as easy as possible for treatment plant staff is an important consideration. There's a potential to use both recycled water and biosolids, and Todd talked about MWMC, which was driven by biosolids use. Curtis is going to talk about Woodburn, which was driven by recycled water, but both of them have the opportunity to use both of those resources beneficially. The high water and nutrient utilization capacity I'll get into a little bit more, and then the buffer issue. There was some discussion earlier about male and female clones. Typically, all these sites focus on male clones because of the potential for that cotton that's generated to potentially play havoc with the wastewater treatment process. You don't want that cotton overloading your clarifiers. So like any other wastewater treatment process, you need to understand the whole system and manage it as a system. And because this is a natural system out in the environment, which is very complex, there's a lot of analysis that needs to go into site selection and site management. Location factors, the specific site soil and drainage conditions, making sure you're not in a too poorly drained or wet site. The climate conditions which affect the irrigation water demands. The water nutrient source factors on the recycled water and biosolids quality coming at the system, the application methods, and then a whole host of tree management factors. All of these need to be looked together as a system to be able to ensure responsible environmental management. So an example here, again for Woodburn, where primary focus was that effluent diversion away from river discharge to meet an ammonia limit. So with a little bit over 2 acre-feet per acre per year, 28 inches, application, effluent quality with total nitrogen content of about 10 milligrams per liter, you're applying about 65 pounds per acre per year of nitrogen. With a 215 pound per acre plantation average nitrogen agronomic loading limit, that creates an opportunity to beneficially reuse another about 150 pounds per acre of nitrogen contribution from biosolids, which in this case is about 3 dry tons per acre. I processed some Agromet data as a local agricultural weather network data across the Northwest to evaluate net irrigation water requirements across a range of different climatic conditions, which we have here in the Northwest, very wet on the west to very dry on the east. And you can see here that there is quite a range. Columbia Basin up in Hermiston, you're looking at about 40 inches net irrigation water requirement a year. You go out to a coastal site here, Bandon, and it's 15. It rains a lot. You have a shorter summer period where you have a need for that supplementary irrigation. In the Willamette Valley, about 24. So, there's almost a threefold difference within the same state. So obviously the site factors are an important consideration in planning one of these systems. I think Lou shared a similar graph before this, just the net irrigation water requirements with tree age as they're initially planted. The demand is low. That grows with time as tree canopy closes. Once you get tree canopy closure, you're looking at that top line until harvest. But once you harvest, then you're resetting the deck back down to the bottom. So if you look at this system operating to meet a permit limit and the capacity of that system driven by the net irrigation water requirements averaged over an entire stand, that harvest rotation and the impact on total system capacity is an important consideration. Along with that comes all the harvest factors too. If you have a small site, you can only dice it up into so many small pieces before individual harvest units become so small they're probably not economically viable units. So this, along with harvest planning, are important considerations. Relating those irrigation water demands back to kind of a wastewater treatment plant operator perspective of how many acres per MGD discharged of poplar trees do I need for one of these systems? If you look at traditional on-demand scheduling, applying water just as it's needed throughout the entire irrigation season here in the Willamette Valley, you're looking at on the range of 125 acres per 1 MGD utilization. Because poplar trees are deep rooting, once they get established, deep rooting, have large root system and root mass, and soil water storage reservoir to draw from, you can deficit irrigate poplars once that root system is tied into deeper water reserves. Deficit irrigate it through the early season, catch up with that lack of irrigation early in the season, refill the profile, catch up with ET during that peak period, like in the case of Woodburn, where their irrigation season is essentially July and August, but trees are needing supplemental irrigation water from April through October. And then cut off irrigation at the end of that period, allow them to draw off that reservoir. With that sort of approach, you can drive that 125 acres per MGD down to about 80, 85. There is a wide range of data in the literature on poplar nitrogen uptake rates and recommended agronomic nitrogen application rates. And poplars do take up a certain amount of luxury nitrogen consumption if provided. You can see rates here, from 75 pounds per acre per year up to almost 350. The recommendations we typically go with and that DEQ has been comfortable with here in Oregon are the Washington Department of Ecology guidelines, which start at about 50 pounds per acre per year, go up to about 240 maximum. Again, tied back to that plantation, harvest, and replanting strategy, you both have a reduction in water utilization and nitrogen utilization in those early years. So need to plan ahead for that and be able to make sure that the system can maintain the capacity that the compliance requirements dictate. So a few important agronomic factors. The primary goal is to maximize that tree growth for high rates of biomass relating to nitrogen consumption, high leaf area relating to water use, getting that canopy closure early. Selecting proven varieties is important. We've had some discussion about that today. And again, that integrating the plantation management plan and rotation age with the final products that are being targeted. Good soil prep and early weed and pest control and water management are really key. Is that first 3 years is where the sites typically, if they're going to have problems, they're going to have them then, and if you're going to have a failure, it's going to be then. So once you get past that point, it's not completely out of the woods, so to say, but it's definitely lower maintenance past that point. So paying close attention to that period is important. And then thoughtful irrigation, water, and nutrient management throughout that growth cycle. Just have 2 more slides here. In terms of irrigation system factors, the irrigation system has to be fully integrated with the treatment plant operations to make it as easy to operate as another treatment process in the plant. And to make that system sustainable to meet those discharge goals that its intended purpose was designed for. There are a lot of components that go into those irrigation systems, and the devil's in the details there, making a system that's compatible with the overall management of the site, not only the day-to-day irrigation scheduling and application, but being able to pull that system back for harvest, being able to redeploy it as needed, and being able to apply the quality of water that's needed in the quantities and at the right timing. And then just a final slide here to leave a few additional concepts. Providing conservatism in the design is really key. Expect the unexpected. Blowdown happens, things happen that might impact your overall system capacity. If you have a little bit extra area available, it allows you to absorb those changes. Every site's different, and soil and climate factors, tree plantation management. So tracking the actual performance of that system with, at a minimum, at least here in Oregon, soil nitrogen is now required for any biosolids application site, not so specifically for recycled water sites, but it's a good idea to be tracking that over time and really understand that system performance. Your maximum application, sustainable application for that site may not be up at the recommended maximum rates. It could be something lower, so it'd be good to know that. Again, I can't stress enough that planning for that low nitrogen utilization and really forecasting what the total plantation demand is, both for nitrogen and water, in response to harvest cycles, and then maximizing biomass production rates, again, tied back to that site performance. If you can sustain a vigorously growing, healthy system throughout its harvest rotation, you're likely going to be doing pretty good on water and nitrogen utilization. And that's all I had to share.